Thank you very much, Fred, for that wonderful trek, however briefly, through cultural evolution, and that does, in fact, bring us to the here and now. We go directly to our next speaker. Jill Tarter is an old friend. She is basically a radio astronomer who has devoted a fair chunk of her career toward a committed, passionate search for extraterrestrial intelligence. She hasn't found any yet, hasn't made contact yet, but I started to wonder last night as she was in the air, coming from San Francisco to Boston, and Boston Center, that's Logan, began picking up all those radar ghost images that maybe they are around us. Her background goes back to Cornell as an undergrad, engineering physics, then on to Berkeley for a doctorate in astronomy, where I think it was in her doctoral thesis, she can tell us correctly or me or otherwise, that it was there that she coined the term brown dwarf that we've been talking about as a candidate for dark matter in many of the previous talks. Jill is currently the holder of the Barney Oliver Chair, a very prestigious position at the SETI Institute at Moffett Field outside San Francisco. She's also the director of SETI Research. She has a long list of publications and an equally long list of awards, but what most impresses me and what I find most admirable about Jill is that she's also found time over the years to not only conduct this search and to lead the United States in this search, indeed the world in this search, but she also finds time to speak to the public, to speak to kids, to speak to teachers. She's also a co-author of many important educational products, including Voyages Through Time, which is a similar product to the one we've been giving you out in this series here. And yes, finally, it is her work that is portrayed by Jodie Foster in the movie Contact. Jill Tarter from California.
Well, it's a real pleasure to be here. I'm a big fan of the Wright Lecture Series and the Wright Center in general. So let's start. 1959 was a very, very important year because it changed fundamentally the entire approach to trying to answer this question, are we alone? And I'm going to actually look at the clock, 50, okay? So I have to be finished by 25 after. All right? For millennia, we've asked this question. Since the earliest humans, we wanted to know how we fit into the cosmos. Is there anyone else out there? Are we alone? And all we could do was to ask the priests and the philosophers and other wise people. And every answer they gave us came back in terms of some belief system that was in vogue at the time. And over history, the prevalence of extraterrestrial life has been cyclical. At times it was in favor, and other times it was not. But it was always somebody's belief. Well, in 1959, that changed. The publication of the first scientific paper on SETI, authored by Philip Morrison and Giuseppe Cocconi in the journal Nature, made that change. And Frank Drake made the first observational experimental search for life beyond Earth using a small radio telescope at the National Radio Astronomy Observatory. And since then, SETI has been about doing the experiment, trying to answer the question as part of an exploratory science and not on the basis of belief. Now, we have to continually remind ourselves as we try and do the experiments that we have to do the experiment correctly. We have to figure out what the right experiment is, and we have to interpret the results appropriately. Okay. SETI is, in fact, embedded within a very interdisciplinary suite of scientific explorations today called astrobiology. And while most of the other astrobiologists are out there looking for biosignatures of life, early life on this planet, life on Mars, perhaps deducing in the future the existence of some biosphere on the surface of a planet orbiting a nearby star, SETI's involved with the search for technosignatures, the evidence of technological civilizations. Now, so we really should call it SETT, all right, the search for extraterrestrial technology. But SETI has a lot of brand recognition, and so we'll continue to use the misnomer, the search for extraterrestrial intelligence. Oops, come on. Okay. There's a general feeling out there that many people will suggest that microbial life might be very prevalent in the universe, but intelligent life might be rare. There are no data yet to either support or refute that claim, and maybe we'll get into that in the panel discussion later on. But in fact, intelligent life may be much easier to find than evidence of microbial life somewhere else. For one thing, intelligent life may occupy a lot more territory than microbial life because it may have engineered that territory, and it may be no longer associated with its place of origin. And what we should do is look for evidence of someone else's technology however we possibly can, given every opportunity. And this idea of looking for someone else's technology is often called astroengineering, and I'm going to run through a couple of examples of astroengineering that have been suggested primarily in the science fiction rather than the science literature, but science fiction has a way of turning it in time into science reality. So I think I'm going to, can I put your laptop lid down? I seem to be blocking. All right, fine. Matryoshka brains. We bioengineer ourselves and our environment in such a way as to make bigger and bigger and bigger computers until our bioengineering dominates our universe. Seyfert galaxies, these amazing galaxies with explosions at their centers, were once quipped by Arthur Clarke to be the industrial accidents of the cosmos. We actually have a more plebeian explanation of them now. Dyson spheres. Freeman Dyson said an advanced technology won't want to let all of its starlight get away. It will build and engineer a structure to capture it. Gamma ray bursters. Someone once wondered, actually this is science, this is a paper that was published, taking all the early gamma ray burst data, these rapid flashes of gamma rays, and someone tried to line them up in four-dimensional space-time to see if these might be the accelerations of a photon annihilation rocket, matter and antimatter annihilating and giving you half MeV photons, gamma rays. The question about whether, indeed, if a civilization uses nuclear fission as its main power source, how they would dispose of fissile waste. One safe thing might be to dump it into your star, in which case we'd see out there a solar-type star with an unusual abundance of some rare earth elements. And Przybylski's star, in fact, is one such, but so far nobody is trying to explain that star for real as a fissile waste dump. All right. Methane on Mars. Methane in the Martian atmosphere. We're seeing it. It might be due to volcanic activity in a planet that we did not think was geologically active. It might be due to subsurface methanogens. That's really cool. Or, in fact, maybe it's somebody's engineering project. If you did fusion rather than fission, you might end up having a problem with a little bit of tritium leaking out. And if you were to use radio telescopes to look at the universe at the equivalent of the 21-centimeter line for normal hydrogen, and you found such emission anywhere except right next to a very recent supernova, you'd be very surprised because tritium has a half-life of only 12 and a half years, and so this might be another way to see evidence of someone else's technology. How about a monolith on the backside of the moon when we get there to explore? Or some transmissions from a planetary-wide system of of radars, essentially beacons for those civilizations that occupy more than one system in their planetary system. Or, okay, here's something that was proposed by Eric, I've forgotten the name, our friend and colleague from Boston University. Mike Papagiannis said, oh, well, what about an asteroid, double asteroid? That other part of the system might be a spacecraft out there mining our asteroids, or an asteroid that disappears would even be another example. Well, actually, we found double asteroids. Here's Ida with its little satellite dactyl. And actually, no one that I heard when this was actually found suggested that that might be someone else's spacecraft out there mining the asteroids. But it was an idea early on. Long-delayed echoes, spacecraft that are put in relatively stable gravitational parking orbits somewhere in the Earth-Sun or Earth-Moon system, these so-called Lagrange points. We've actually looked here. I think we would have, with the kinds of experiments that we've done, been able to rule out the existence of a huge Starship Enterprise that was big and bright and shiny. But if it was dark, or if it was small, or if there are nanoprobes in the solar system, forget it. We haven't looked hard enough or well enough to have found such things. And finally, when pulsars were first detected by astronomers in Cambridge, England, they were dubbed little green men because we didn't immediately believe that nature could produce such beautifully regular signals. It took a little while to remember that 30 years before, the theoretical astrophysicist had predicted exactly this sort of thing. All right, so a bunch of astroengineering projects. And the thing that I'm impressed with all of those is that we don't really have a way of systematically going and searching for them, right? There's just, if you set out to set up an experiment that could possibly have a significant null result for looking for things that we ourselves don't do, that's technology that's beyond our means, we can't systematically plan a search. So in fact, we should be looking for all of this stuff, but we should be doing it as part of astronomy. When we look at the universe with all of our different tools, we should remember that little bit of scruff, as Jocelyn Bell called it when she first found pulsars. If there's something anomalous, don't just edit it out of your data. Don't just keep it in your bottom drawer, but at least spend a few think-ons trying to figure out whether or not it represents perhaps some unexpected evidence of someone else's technology. So systematically, it's hard to search for advanced astroengineering projects. But in fact, there is a way to search systematically for electromagnetic signals, because this is a technology that we employ ourselves, so we can set up the parameters and say, if I could do this in this wavelength with these kinds of technologies, I could detect the equivalent analog of a 21st century Earth anywhere within the Milky Way galaxy. And if you could conduct such a search, and we're very, very, very far away from doing that yet, but if you could conduct such a search and you came up with a null result, that kind of result would be significant. So in fact, there are three ways that we can think of right now to search for electromagnetic signals, and they came out of a workshop that was held at the end of the last century. That sounds scary. It's shivery to say the end of the last century, but it was, 97 to 99. We held a series of workshops at the SETI Institute. We published the results in this volume, SETI 2020. We basically said, what should we be doing for the next couple of decades? And we concluded that looking for radio signals still makes sense. We've been doing it for 40-some-odd years, but it still makes sense. However, now that we're 40, now that we're getting to be grown-ups, we ought to have our own telescope, and we ought to build it in a different way, in a way that we could afford. And so that was our first conclusion. Our second conclusion was Charlie Towns told us back in the 60s that we ought to be looking, as well as looking for radio signals, we ought to be looking for optical laser pulses. And we said, yeah, Charlie, that's a great idea, but you know, at the bottom of it, what you need is a technology to count photons really, really fast, like within a nanosecond. And although the kind of activity, you don't over-engineer. You only put as much power in it as you need to reach your audience, and if it's unintentional, that is, if it is not intended to reach across the stars, only your local consumers, then it's probably going to be weak and hard to find. But deliberate signals, now you have a different game. All right? If you want to make a signal that somebody out there can detect, you could make it be sort of almost natural, the kind of thing that an emergent technology, when they woke up and opened up their multi-wavelength eyes and looked at the universe, would capture in their nets. It might take them a while to figure out that they had your signal, but you can be pretty sure that they would find it. So pulsars are an example. Pulsars have different periods, very, very, very precise clocks. All right? What about a pulsar that changed its period from one precise value to another and then back to the first and then back to the second? That would catch an astronomer's attention and might be a very detectable way of manufacturing a signal. Right? There's another extreme for deliberate signals, and that's the kinds of signals that nature can't make, but only a technology can. So this idea of twisted light actually modulating the rotation state of photons, or signals that have a time frequency bandwidth that's close to unity. Right? The uncertainty principle tells us that the amount of frequency space, delta nu, occupied by a signal, and its time duration, when you put those products together, they have to exceed 1. Now, that's the red curve. Our technology, mainly for economic reasons, can produce signals that are very close to that limit. But when you think about natural astrophysical emissions, they're in a totally different part of the graph. So time bandwidth products near unity is the kind of signals that we've been looking for in SETI. Short pulses will be broadband, narrowband signals will be long duration and continuous. And again, I emphasize, we are looking for our own, we are using our 21st century technology because that's what we have, and we're looking for other technologies that are like ours. We've had microwave searches on the telescope for about 40 years. Very quickly, I'm going to show you pictures of telescopes that are working today. This is the Serendip system at Arecibo that provides data for SETI at Home, the world's largest distributed computing project. Paul Horowitz had a program called Beta at the Agassiz telescope right here in Massachusetts at the Oak Ridge Observatory. The wind picked the telescope off and dropped it ungracefully on the ground. Paul's been involved with optical SETI, so this telescope has not yet been straightened out, but it will be and back on the air. A clone of that system operates in Argentina. This is the Parkes telescope in Australia, which often operates with a 13-beam focal plane array, and 2 of those beams have piggyback Serendip systems on them. And here's a Project Argus in New Jersey. It's an amateur attempt to look for transient signals. And then the project that I worked on for a decade, the SETI Institute, Project Phoenix, which did its signal processing in real time and always used 2 widely separated telescopes to discriminate against our own interference. Optical SETI, as I said, it got started with that SETI 2020 report. The key is not only very fast photodiodes, fast photon counters, but using 2 of them in coincidence so that you can discriminate against the background events from high-energy particles interacting with the glass in the telescope. The first one was built for this 30-inch at Leuschner at Berkeley. Paul Horowitz copied that with his graduate students. You have, it turns out, hot, muggy August nights in Massachusetts, and some of these photodiodes tend to break down. So Paul had an unacceptably high false alarm rate. So he called up his friends at Princeton, had them refurbish this telescope on campus, and very clever, they take advantage of the fact that there's 1.6 milliseconds of light travel time between Harvard and Princeton. And so a really valid event from a distant star when these 2 telescopes are looking in the same place is 2 photodiodes going off there and 2 photodiodes at Princeton, and that kind of time difference between them. Small dedicated telescope outside of Sydney, and this is the best of the optical SETI systems built at Lick Observatory by this young lady who had, as an undergraduate, this was her senior thesis project. She's a not very typical student. She also ran a business building Van de Graaff generators for science museums. But this is the best system because it has not 2 photodiodes, but 3 photodiodes, and therefore essentially 0 false alarms. Unfortunately, also 0 positive results as well. That's the story of SETI so far. And Jeff Marcy has reanalyzed all of this absorption spectrum data that have been taken from Lick down here and the Keck telescopes on Hawaii, looking for extrasolar planets, and he's reanalyzed that data looking for narrowband laser signals. All right, so that's SETI on the telescopes today. We're looking at SETI tomorrow. Right? Paul Horowitz is about to inaugurate, again out at Oak Ridge, an optical SETI sky survey system. And at the Hack Creek Valley in Northern California, I'm about ready to turn on the Allen Telescope Array as a partnership with UC Berkeley. And I'm going to spend some time, yeah, I still got time, telling you about this telescope because I think it's really cool. All right, but what about, and both of those have been done with private funding. Right? That is the story of SETI since 1993. The day after tomorrow, we may be able to build this omnidirectional SETI system. The receivers are very simple, spiral antennas, digital radios, but what costs is the computing, all of the beamforming and the large spectral analysis for all the directions on the sky. For something that has, think of a tabletop, think of your dining room table. Something with about as much collecting area as that would require something like 10 to the 16 operations per second of computing, 10 petaops. It's coming, it's just not yet affordable. So this is a telescope for the day after tomorrow. And optical SETI also has day after tomorrow. We'll look at ways that we can piggyback on large optical systems that are being planned for the future. And in the radio spectrum, the radio part of the spectrum, I'm going to tell you about the Allen Telescope Array. There's an international project that's trying to build a telescope that's yet 100 times bigger than that. It'll probably get built, if at all, about 2020, about the time that report runs out. And for SETI, the idea is that with 100 times more sensitivity, I can look 10 times farther away. And so here's our picture of the Milky Way galaxy, right, or half of it. And this is to scale. So right up there, you can see a little pink dot. All right, that's the 150 light-year sphere that I spent 10 years with Project Phoenix analyzing the stars, exploring the stars in that volume. In the next decade, with the Allen Telescope Array, I'm going to look at 1 million stars in that volume. And then 2 decades from now, hopefully we'll have the Square Kilometer Array. And you can begin to see that our tools are finally getting to be commensurate with the size of the search that we may have to conduct before we succeed, if we succeed. Right? So, and the day after tomorrow, we can think about the best place in the solar system to build a radio telescope for SETI, which would be on the lunar far side, the part of the moon that never has the Earth in its horizon, above the horizon. It never has the Earth in its sky. And that means that all of the radio frequency interference is eliminated. And we don't have to discriminate against it. We can shield it with the moon. And of course, half of the time, the far side of the moon is also the dark side. So this would also be a very good place to do optical SETI. On the other hand, we're never going to afford to do it except as part of a large infrastructure for something else. And unfortunately, one of the something else's may be the construction and maintenance of spacecraft at the L2 point at the far side of the moon. And that indeed would do a great deal to degrade the pristine environment there. So we're our own worst enemies. Now, this is a phrase from Phil Morrison, who called SETI the archaeology of the future. And I love it, and I think it's a beautiful encapsulation of why I, in particular, think working on SETI is important. Okay? It's archaeology because any remote sensing of somebody's astroengineering projects or any detection of a signal requires the speed of light. That's as fast as that information can reach us. So by the time we get the signal, we're actually learning about their past. Archaeology. But in fact, if we get a signal, if SETI succeeds, it must mean that technology is long-lived. And therefore, it tells us that it's possible for us to have a future. And there are many things that we're doing today that would indicate the opposite. So it tells us about their past and our future. So let's go into that a little bit. Unless technology in general out there is long-lived, SETI cannot succeed. Right. Here's a cartoon. Time, some measure of technology. Not a lot happened for a while on Earth, and then suddenly we're into this exponential rise of technology. Well, we've never seen in nature an exponent that didn't turn over, didn't reach some carrying capacity and saturate. So that's why I've drawn it this way. But in fact, maybe technology is an example of something that will continue to exponentiate. This is what futurists refer to as the singularity. But my conclusion is the same, whether it's this or this, and that's that if technology is long-lived, we're going to catch them in the long-lived part of their existence. Statistically speaking, we're not going to catch them in the short pre-technology or early technology phase. On the other hand, if that's the correct cartoon for technology, it increases for a while and then is either turned off or turns itself off by some disastrous consequence, then there's nobody out there that is spatially and temporally coincident with us, and we will not succeed. And anybody, if we do succeed, anybody we find will be older than we are. So we're talking about the archaeology of the future. All right? And Contact had the right idea. We need a better telescope. That's what Jodie Foster is saying. Her next sentence is, and now all we need is the money. All right? And that tomorrow's telescope is going to be the Allen Telescope Array. I've already said it's a partnership between my institute and UC Berkeley. It'll be made by arraying 356.1 meter dishes. It's be located at Hack Creek in Northern California. It's inexpensive to build relative to a traditional telescope. And the great thing is it does SETI and cutting-edge, fantastic radio astronomy simultaneously 24/7. So this is a beautiful survey instrument for SETI and radio astronomy. And we have to do it cheap, right? So we need a construction facility. Well, ours is a tent. And we kind of got behind Homeland Security in the delivery date from the vendor, and so he decided to deliver it on the day that it was a snowstorm, and we had to take it down again and wait, and now we could finally finish the construction. And this is what happens in the tent. Right? A small team of technicians and engineers put these telescopes together like Tinker Toys. It's all kitted up and it's all carefully just in time, right, delivered to the observatory to be put together. And this is number one, right? And is it going to fit out the door, right? All right. Yes, it does fit. And it takes about a day and a half to build one of these in the tent. And it takes about 20 minutes to drive it out on the lavas and put it up on the pedestals that are already implanted. So that's how we build our telescopes. By the end of this year, we'll have 42 of them up. That is a funded project, and we'll start doing science with them. And then sometime 2007, 2008, just depending on how rapidly we can continue to raise the funding, the Hack Creek Valley will be filled with these rather unusual-looking tall flowers. And I hope by then I can afford to buy him a better-looking sweater. But this is what we're going for, and it will be an amazing array. The science and cosmology that this antenna will produce that we can count on is really exciting, and in fact, it may finally give us evidence of someone else's technology. So anyone who, that went by much too fast, right? If you happen to have $100,000 burning a hole in your pocket, you can buy an antenna, and we would be delighted if you wanted to do that. All right, so I've been talking about finding someone else's technology. Always the question comes up, should we be, if we're expecting them to transmit, shouldn't we be transmitting? Okay? And if we're going to transmit, we have to answer these hard questions. Who will speak for Earth, and what will they say? Well, you have to first, when you think about it, understand that we're in a very asymmetric position relative to any other technology in the galaxy. We may be the only technology in the galaxy, but we're certainly the youngest. Anyone less technically capable than ourselves is undetectable over interstellar distances. And if we're the youngest, we should do the simple job first and the hard job when we can. So transmission requires a long-term commitment and global cooperation and coordination, and we're not there yet. We are just not capable of doing that. And so SETI 2020 decided that at least for the near term, a transmitting program shouldn't be pursued, but they are mindful that after we grow up as a civilization and mature and can deal with long-term commitments and global cooperation, that transmitting may be in our future. Okay, well, how do I know that we're not grown up enough to do this job? Well, I used Google, right? The best research tool that anyone can come up with, all right? I asked Google for the number of times that 1, 2, 5, 10, 20, 50, 100, 200, etc. year plan was mentioned. And these are the reports back, right? Now, here's the number of hits I got when I searched on my name. And I would contend that anything that we're not talking about on Google more frequently than my name is not something that we're taking seriously, right? So that look where that breaks, about 100 years. And now the hits are getting low enough in number that you can actually look and see what the content of them is. And the only thing we're really discussing is science fiction or religion when timescales of 100 years or more are talked about. There are a few exceptions. One, the environmentalists have begun to take a long enough view to talk about 500-year consequences. The Y2K, 2000, right, got a lot of hits, and 10,000 shows up because of the discussion of burying nuclear waste at Yucca Mountain, and also because something called the Long Now Foundation. Long Now Foundation is trying to build a clock that will work 10,000 years from now, and with that clock there will be a library of humanity. And so they're the first indication that I've had that there are organizations that can begin to discuss these long-term plans. And they can answer these questions. Who will speak for Earth, and what will they say? Who will speak for Earth? Well, the people who wind the clock, and what will they say? They've got the whole library of humanity to work with. So the Long Now Foundation, which has actually bought this mountain in Nevada, on which I think very poetically there are these 4,000-year-old bristlecone pine trees. The clock will actually be built on a monumental scale inside this mountain because that's about the only way you can get it to last for 10,000 years. And I'm wondering if, in fact, we can't find some way to link transmitters with that clock for perhaps the first long hello. And so I'll end by saying I don't know whether SETI will succeed or not. I don't know the answer to the "Are we alone?" question. But Phil Morrison and Giuseppe Cocconi, I think, had the wisest thing to say. They said, this is the last sentence of that paper in Nature, probability of success is difficult to estimate, But if we never search, the chance of success is zero. So stay tuned, because we're going to keep searching. Thank you.
All right, as is traditionally now the case, we'll take a seventh inning stretch for 60 seconds. You can get up out of your seats, but don't change your coordinates, and we'll form the panel. We'll be right back. And Jill to talk to each other. The whole objective, from my point of view, is to expose the cultural side of science, or the subjective side of science, by peeling away the curtain and watch and listen to two world-class scientists talking to each other. But I'm in the middle here, just in case it gets interesting. I'm an Emersonian after hours, and I remember 150 years back, Emerson's colleague or friend in England, Thomas Carlyle, telling me at dinner, said something to the effect that if alien worlds be inhabited, what a scope for folly, but if they not be inhabited, what an incredible waste of space. So we have this issue. We have a cultural anthropologist with us now who studies civilizations that we see around us, some of whom have been successful, others of which have collapsed, to use a Jared Diamond term. We have another scientist, Jill Tarter, who attempts to seek out other civilizations out there in alien worlds. I've been reading Collapse, the book by Jared Diamond recently, and it's a very interesting, however you take it, it's a very interesting work, exhaustively researched work of some 500, 600 pages, in which he suggests and documents reasonably well that a lot of civilizations that have preceded us, and not dumb civilizations by any means, pretty smart civilizations, haven't made it. They've collapsed. They've collapsed either because of self-inflicted environmental degradation or natural climate change or disastrous trading partners or unfortunate social responses they've had to their condition. I'm wondering, as you look out and you yet have found nothing, though I also remember Phil Morrison saying that you got to search for 1,000 years before you really start to get concerned about it. But you have not found anything. I'm wondering if you could talk a little bit about whether it's the natural scheme of things for civilizations not to make it much more beyond our technological level of development, simply because those global problems crawling up all of those exponential rising curves are just too much. Rapid change for even a sentient being like us, or anywhere in the universe, to get their act together, to develop that sense of global ethics, planetary citizenship, evolutionary ethics, as I like to say. And maybe it's the natural scheme of things, that your civilizations won't extend much more than what we've come to know and like and love now, and that's the solution to the Fermi paradox. We don't see them out there because they're not there, because nobody is able to culturally survive beyond our level. Talk a little bit about that, if you would. Well, what are your feelings about that? Will we be able to get our act together and survive much longer? Should we expect other civilizations in the universe to have done better than we are doing?
Well, I think if we just look at our own, let's call it civilization, there are two options. One is that we find new energy sources that are almost inexhaustible. And it's not impossible, but perhaps not very likely right now. If we find them, then we may be able to continue along this route for quite some time.
These energy sources could be used for ill will as well.
Could also be used, yes, that's for sure, but it may allow us to do better. But if we don't find them, then it's clear that it's either go extinct or adapt. And will we be able to culturally adapt? Or will
Quickly enough.
Quickly enough, yes, that's for sure, instead of fighting over ever scarcer resources.
Because for the first time in history on this planet, these are global problems. They're not. World War II was not a world war problem. Now we are facing global problems, and we must solve each and every one of them. If we fail to solve one single global problem, we're extinct.
Well, or at least
very
much reduced.
Very much reduced.
Yes, I agree. That's certainly possible.
You've thought a lot about this.
Well, actually, I heard a really interesting lecture last week, looking at, and you had some similar graphs, the per capita energy use, right, globally, and then there were other charts, which were essentially measures of the quality of life, all kinds of different measures. And once you get beyond maybe 100 or whatever units were being used, there's no measured increase in the quality of life. Yet, in these units, something like a first world country like the U.S. is using 400. And the undeveloped countries are limping along with 10s and 20. So it's not, yes, we have to find new energy sources, and yes, we have to do it quickly, but we also have to redistribute to realize that there's a certain amount of energy that gets you the good life, and it doesn't get much better even when you use more energy. So that redistribution is a possibility, and that's going to be a real hard sell psychologically, I think. But I think people are beginning to talk about it. I pointed out at least the environmentalists are beginning to look in the 500-year kind of look at the long now future.
I thought you were going to say get beyond the Earth, in the sense that if we stay on the Earth as a civilization, we have all of our eggs in that single basket.
Well, I mean, we're going to lose that game, we know, simply because there's going to be another asteroid coming along.
Absolutely.
Even if we solved our global energy usage, even if we controlled our population, even if we got this world just right, we're going to lose it.
So probability works against us as long as we're residents of the Earth. But once we begin to go beyond the Earth, disperse our species into larger realms of real estate, probability theory starts to work in our favor.
Right. And so, but we first have to find out, I think, whether there are any indigenous Martians before we go terraforming Mars.
Well, what's your feeling on that?
I have a feeling, certainly there are arguments that can be made that there are still subsurface liquid aquifers on the planet Mars, and life started so quickly on the early Earth that it might well have started on Mars, might still be there, and I'm really curious about that methane.
Yes. That was the gas detected by the European spacecraft.
It was detected
Orbiting
in two
around,
different ways. It
yes.
was also by Mike Muma and Goddard with a ground-based telescope.
Ground-based telescope. Okay.
Can I ask you a question?
Please.
Well, given that you haven't found any clear signals for the last 40 years or so, can you say anything about, let's say, the radius from Earth that you would sort of rule out the existence of civilization?
Those were those circles she had.
Well, no. The spheres that I had on the graph were not the distances to which we could rule out a civilization. They were the distances to which we have and could conceive of in the future interrogate a particular star for a particular type of technology. So we could tell you that on a particular afternoon in May of 1998, there was no transmission at a particular frequency when we looked from the telescope at Arecibo at a particular star. Does that mean there's no technological civilization on that star? No. Right? Our cosmic haystack is 9-dimensional, and it takes a while to work through all of that. So I think that's where Phil Morrison got the thousands of years.
Yeah.
So I'm not worried about Faraday's paradox. We haven't looked. Faraday's paradox only becomes a paradox if you can say they're not here, or that there is a great silence.
Yeah, everybody understand what the Fermi paradox is? The essence of it is that if they're out there, why haven't we seen some evidence of their presence? Briefly, he said, where the hell are they?
Where is it?
What are the implications of us being alone? Would that bother you? Would that make your subject more important or significant? Would it put more of a responsibility on us to get our act together and to survive? If we are the only technological, sentient beings in, let's say, this part of the universe, or maybe the whole universe, what are the implications of that? Equally significant, it seems to me, as you are making contact.
That's incredibly correct.
But we'll never know if we're actually alone.
No, you can't prove the negative.
You can't prove the negative.
Right.
Well, I cannot speak for other people. I can only speak for myself.
That's fine.
And I think that I would not really care a lot whether we are alone in the universe or not, but I do care for the future of my kids and for the future of other person's kids. I think that's the most important reason of why I think we should start to stabilize the situation and not whether we're alone or not. And I would actually be a little worried if we were to find civilizations not too far away because they might be hungry.
We told you not to say that, didn't
But you know, maybe our DNA is indigestible.
It
Maybe
is
it's a
interesting
different
if
chemistry.
if the laws of anthropology, which you study, are as universal as the laws of physics and chemistry, then it's not inconceivable that they will do what we have done to other lesser species on this earth.
Yes.
And it's not very positive. Let's begin to broaden the discussion a little bit. Laura is over here, I can see her, and Sherry is over here, a couple of right fellows with roving microphones. They can identify people, I can identify. We can't see you all that well from here. There's a gentleman right here in the front row, Sherry, in the yellow jacket. We'll start off with this gentleman, and then we'll make our way back up to the bleachers.
We noticed with hurricanes that people become very generous to other people. I wonder if we perceive the problems that all of us in the world are facing, whether that will change the attitude of people towards other people. We spend a lot of time in civilized society killing off other people and opposing other civilizations. What's your view on this? And there's a second question I have, and that is, can societies in, say, Africa jump phases? You're talking about phases you go through in history. Can they jump into the technological world, or do they have to go through phases? It's two very different questions.
Let's give Fred a chance first.
Well, I think what you can say in human history that are what Dutch sociologist Abraham de Zwaan is his name, calls widening circles of identification. That when people lived in small groups, tribes, or whatever you call them, they would only care about their own tribes, and other people would not even be seen as people. And what we see more and more that people are identifying with people farther and farther away, or people that are different from what they themselves are. So yes, that's certainly a trend that we're seeing, but not always. The opposite happens also. People start to define others as lesser, inferior, more dangerous, and as a result, there's more conflict. So I think both trends are happening at the same time. But yes, it's all globalizing. That's for sure. What was the second question?
Can you switch from being...
Can you jump quickly?
Oh, the jumping off the
African
phases. Well,
right,
it
right.
depends. For example, apparently if you were already a state society, which reasonably advanced levels of technology, then it is not so difficult to jump into the industrial phase. That's what we've seen in Asia, for example. But if you're not, if you just are organized more along, let's say, tribal lines, then apparently it's a lot more difficult to do this. And that's not the only reason. A lot of the areas where, until recently, there were such tribal societies, are usually not very good for starting industries. For example, let's say in the middle of Africa, I would not start an industry in an area where it's dry for half of the year, so there is no water. As a result, very hard to run any industry because all industries need lots of water. It's very hard to get your products in and out. So it's also the geographical circumstances that make it sometimes very difficult for people to jump phases. So there's both social and ecological reasons, I think, that work for or against this.
Yeah, actually, you're probably not surprised to hear me say that I'm an optimistic person. Otherwise, I wouldn't be working on what I do. And one of the most, I think, fundamental and important reasons to work on the search for extraterrestrial intelligence is if we found another independently evolved civilization out there, it would hold up a mirror just as your picture from Apollo 8 did.
Yes.
It would hold up a mirror in which we would have to see all of ourselves as one species, as all human, and it would trivialize the differences among us that we find so contentious today, because we would be all so similar when compared to this other, very different.
sort of unifying effect.
I would think so.
Yeah. Laura's got a question somewhere.
Yeah.
through
Could
here.
you speak
Where
to
are
the comment about the inevitability of the asteroid that you mentioned?
Oh,
Why?
you worried now.
Got you thinking.
Yes. Throughout the history of the Earth, most notably recorded on the surface of the moon,
Right.
we have been bombarded by chunks of debris that are left over from the formation of the solar system. A lot of them are organized in what we call the asteroid belt, a bunch of rocks that are orbiting between Mars and Jupiter, and those orbits are pretty stable, except that occasionally something somewhere perturbs an asteroid from its orbit, or we have even a bigger reservoir of leftover building blocks of the planetary system out beyond the most distant planets. Something perturbs them, and they fall towards Earth. They fall in towards the sun, I should say, and the gravitational interactions sometimes bring them in contact with the Earth. Now, it happened very, very frequently up to about, for the first 3.5 billion years of the solar system's history. And it has happened less frequently since then. But certainly the extinction of the dinosaurs 65 million years ago is a classic example of a really bad day caused by an asteroidal impact that was kilometers in size. And we are now trying, there is a project called SpaceGuard that is trying to catalog all of the near-Earth orbit and Earth-crossing bodies out there that are bigger than a kilometer in size. And we constantly keep finding new bodies. We keep detecting new pieces of real estate out there. And some of them, so far, none definitively, so you don't have to worry about it tonight. But some of them appear when we first detect them as if, when you project their orbit into the future, they will collide with Earth. When we've gotten better, more accurate orbits, in fact, none of them. There's one that about 20 years from now, there's a keyhole event,
Right.
which if it passes through a particular region of Earth, or a particular region of space, may get focused
But there are 21 Apollo asteroids that are well documented and well known. They are Earth-crossing asteroids, and they eventually, if not perturbed, will have to hit the Earth. And they're pretty good-sized rock. But that's probably way in the future. But statistically, unless they're disturbed naturally, or unless we as a civilization literally go out there and perturb them in a different orbit, and we might even have that kind of technology almost present now to do so. But these Apollo asteroids are Earth-crossing asteroids, and they will hit us, and that's almost definitely the natural scheme of things. The motor of evolution has accelerated during periods of the Earth being bombarded. That's pretty well documented. Good question, but I wouldn't quite worry about it yet. How about someone has a question. Sherry, can you get a mic up to there?
You've got
Somebody's pointing up there in the bleachers.
Hello.
Okay,
we go.
deep center field.
Hi.
See where you are. But
This is kind of a two-part question. First, you talked about sending a signal out into outer space and kind of like broadcasting, and I'm wondering if that's such a good idea because you don't know what you're going to track back to the Earth. You're saying, hey, we're over here.
yeah.
And just as the other gentleman was saying, if the civilization was close, they might want to come and eat us. And the other part goes along with, what do you feel about UFOs? Do you actually think they exist? I mean, I know you're looking for signals, but people keep on talking about UFOs being sighted all over the Earth. How does that relate to your
Give her a
study
chance
of your
to answer.
organization? Yeah.
Good.
Okay, UFOs, unexplained flying objects. Yes, they exist. Absolutely they exist. I've seen one. They don't, or at least there is as yet absolutely no evidence that they have anything to do with spaceships coming from somewhere else. We see things that we don't have explanations for. Our visual system is actually programmed to do that. We don't actually see things, we interpret them.
Patterns.
And when there's something that we see that we can't quite understand, we interpret it in terms of something that we can understand. So it's really hard when you're dealing with visual accounts. But so UFOs, there are unexplained phenomena out there. We don't know yet the last word of physics and astronomy. We'll learn more things. For years, there were these anecdotal reports of things happening above thunderclouds that were reported by pilots flying high. It took a long time before we had orbital assets, spacecraft, with fast enough cameras to record what are called sprites and elves. Think about it, lightning traveling up from the top of a cloud, up rather than down to Earth. So that was a new phenomenon that turned out not to have anything to do with flying saucers. So, no, I haven't seen any evidence. If somebody brings me an ashtray from the spacecraft on which they were abducted and examined, if you bring me the data, if there's evidence there, I'm very eager to see it because I want to answer the question however we can. So that's your second question. Your first question was the transmissions. Well, you know what? We've already been doing it for 100 years. This leakage radiation, not deliberate broadcasting. We've only done that really once. No, a couple of times now. They're doing it for money from the former Soviet Union. But our leakage radiation, although our 21st century technology would be hard to find the low level of energy that's in the leakage radiation that we produce, a more advanced technology might be able to, if they were within 100 light years, because that's as far as that information has traveled. So we've already announced our presence. And so deliberate transmissions, again, who will speak for Earth and what will they say? And should we do it, it's got to be a global conversation before we take that on.
Just think of the television transmissions by which we've announced our intelligence.
How do you do these? Right?
Jerry, how about down here in the front row over here in the section 8?
Try a couple of questions. If an intelligent civilization is out there and they're formed at about the same time we did, how would we contact them? Or because you said that when we receive contact, it will be a civilization much older than ours.
Yeah.
What if in fact they formed at the same time? What would the essence of the communication be? That's
and
one
what
question.
if they're conservatively just listening, as we are?
Okay.
Yeah. Second
And the
question.
second question is, I never really thought about this before until tonight. What do the intelligent design people have to say about extraterrestrial life? And are you people wasting your time?
Yeah.
No, actually, I'll answer that second one first because it galls me. We have been co-opted by the intelligent design people who say, well, look, SETI can look out there, and they say they can detect intelligence in signals, so certainly we must be able to see the results of intelligent design in DNA or in biology. And that's a specious argument, and I'm not pleased that we've been used in support of that particular belief system. And in terms of the first question, could we, in fact, detect someone that was our analog? And they would have to be very close.
Yeah.
That's the answer. And so the fact that I say that a detection will come from an older civilization is really a statistical argument. It's unlikely that there's going to be somebody in this huge galaxy, unless it's just teeming with intelligent civilizations. It's unlikely that one that is just at our technical capability would be close enough for us to detect. And now, and not some other time in the 10 billion year history of the galaxy.
We had a question over here. Do you have a mic? Good.
Yeah, I was curious to know, the Fermi paradox also refers to the fact that any reasonable expansion of civilization would have taken around 10 million years to colonize the galaxy if they were so inclined.
Yeah.
And Given, so what do you believe is the possibility of detecting such an expansion of civilization like a type, well, obviously a type 3, which controls the resources of a galaxy, or type 1, which controls the resources of a star? So that's part one of the question. Part two, the follow-on, is just you've remained very agnostic on terms of what you actually believe. You're saying you're an optimist, so I imagine you hope that the result will end up being positive. But what is your personal solution to the Drake equation?
Oh, I don't know the answer to the Drake equation. And I look at this as a question that humans have been asking for millennia. And I happen to live in the first generation of human beings that can try and answer the question experimentally. And isn't that a fantastic way to spend a career trying to answer a question that's been important enough to humans that generation after generation after generation they continue to ask? It's a question that other branches of physics and astronomy and chemistry and biology say is a possibility. The other sciences don't say, here's the reason why there can't be life anywhere else except here. What we know seems to make the universe apparently bio-friendly. So it's a possibility. It's an important question. I think it's a privilege to try and answer it. So I have the best job in the world.
And when Frank Drake was here a few years ago as a Wright lecturer, he had the same answer, that he didn't know the answer to his own equation, but he thought it was remarkable that he could write down that equation and begin to make estimates of what it might mean.
And you asked about the Fermi paradox. Let me actually do the Fermi paradox because there are a couple of parts of it that are important.
Okay.
We say Fermi showed up at lunch at Los Alamos one day and said, so where is everybody? and here's what he meant. That if anywhere at any time in the history of the Milky Way galaxy a technological civilization had developed, then it would be, a blink of an eye before they would develop the technology for interstellar travel. And they would inevitably do this, and then they would begin a colonization process. And whatever model you use, you end up with colonization of the entire galaxy, taking a very small fraction of the age of the galaxy. So therefore, they should have colonized every place, and they're not here,
Maybe they are.
so they can never have been anywhere, anytime. Right? So I take issue with the they're not here part of that statement. And I don't mean it's UFOs, and I don't mean that it's people abducting Ann Alice off the streets or salacious medical experiments, right? What I mean is that we have so poorly explored even our local solar system that I said earlier we could probably rule out great big shiny Starship Enterprise kinds of things from being in our solar system. But these asteroids, these near-Earth orbit things that are only a kilometer and are kind of dark, they show up and surprise us all the time. We find these things, particularly if they're coming in from the direction of the sun. We have to wait till they've gone past the sun and then we can see them. So what about if colonization was done by an advanced technology with nanoprobes, small, sharp, smart machines? It wasn't big, wet, spear-wielding, hungry biology that did the colonization, but something that was an intelligent machine. We wouldn't have found those. Not yet.
That was a point made in the first Wright lecture a month ago, that it's so ironic that what we have in our technological arsenal enables us to find things as small as atoms by way of spectroscopy in space, or as big as stars because they're lit up bright and shiny. But objects that are largely in between atoms and stars, if they're far enough away, there's nothing in our arsenal that enables us to detect them or know that they're there. Very, very interesting. Laura has a mic over here, and there's a gentleman in the middle here. And then we'll go back up to the center field there. You see what my passion is.
I was going to say, these sports analogies leave some of us baffled.
Do you have any predictions on the evolution of artificial intelligence in the next 50 to, say, 200 years?
Predictions.
I'm looking at Fred.
Give it a go, Fred.
Prediction, well, it seems to me that that clearly we're going to be more and more connected to machines, which we are already, and we're now basically connected through machines to other people, the internet, for example. But I guess there will form some kind of human-machine combination. That seems very likely. Where that will lead us, I'm not really sure. We are also able to engineer life more and more. Are we going to engineer human beings to tailor them to fit into machines? Who knows?
Way up in the back, Laura. Oh, unless Sherry has it. Sherry, maybe you can get it. There's a gentleman in the back. Yeah. Okay.
Earlier in one of your graphs, you showed what I learned before is called the S-curve, where something grows exponentially and then cuts off. Now, if we refer to humanity in terms of the S-curve, where we're just going to grow and then cut off, I want both of your opinions on this. Where do we stand there in the S-curve? Where are we on that little graph?
Well, we're certainly continuing on the exponential by all kinds of different measures. Energy usage, just CPU cycles available, and all of this sort of stuff. So we're in that exponential growth part. Whether it's going to saturate or not, I don't know. And in answer to the last question, when we look at that exponential that just keeps rising, people speculate that the only thing that will be able to survive that singularity is engineered intelligence that can evolve fast enough to keep up with this increasingly rapid growth of technology. So our population, actually, when I was growing up, Eric, when we were young, right, the population bomb was the thing that was so scary, right? More than half the countries in the world today are not reproducing themselves. Right. The birth rate is fallen in a way that we never expected back in when I was young. Right. That kind of population control might, in fact, allow us to have a sustainable future population on the planet and get to a usage of resources that asymptotically flattens out and doesn't continue to grow so fast that it destabilizes our entire environment.
Well, we do need to bring this series to an end. I'll note that this series will reconvene next fall in Geneva at the Jean Piaget Center. If you happen to be traveling in Europe, pick up that series. Otherwise, pick it up live on the internet. I want to thank the Museum of Science staff here and the Wright Center staff and fellows for doing a wonderful job and a wonderful partnership. And finally, I think we should all thank Jill and Fred one more time for a wonderful evening.